Написано скоро. О. Так. Здорово. Трансляция идет из 108-й. Какая-то мистика. Да, ну написано Sister Algebras and Compact Quantum Groups. Явно из 108-й. А? Нет, это не то сейчас. Это я там... Ой. Это я там включил и выключил, что ли? Ну что теперь? Все, я все испортил? Ну то есть она идет только по другим названиям. Ну ладно. Ну то есть, в общем, ничего страшного не произошло, да? Так. О, вот она, ура. Нашлась. Ну ладно. Главное, что идет. Кому надо, тот найдет. Okay, so at the previous lecture we began to discuss the basics of commutative Banach algebras. And let's recall that two principal notions, two fundamental notions of this theory are the maximal spectrum and the Gelfand transform. So let's briefly recall how they are defined. We start with commutative unital Banach algebra A, and we consider the following two sets. The first set is the maximal spectrum. By definition, this is the set of all maximal ideals of A. And the second set is the character space, A hat, which consists of all non-trivial characters, that is, of all non-zero homomorphisms from A to the complex numbers. There is a natural map from here to here, which takes every character to its kernel. Well, the kernel of a character is obviously a maximal ideal. Well, actually, this construction makes sense for any commutative unital algebra, not necessarily a Banach algebra. And in the general case, this map is injective. But we proved at the previous lecture that if A is a Banach algebra, then this map is actually a bijection. So, as a result, we may identify, and we will identify these two sets under this map. Next, we equip this set with a topology in the following way. So we know that every character is continuous. Every character of a Banach algebra is continuous. So A hat becomes a subset of the dual space A star. We equip A star with the weak star topology. And we consider the induced topology on A hat, or equivalently on the spectrum. So the spectrum becomes a topological space, and we prove that the space is compact and Hausdorff. Compact and Hausdorff. And now we define the Gelfand transform of A, to be a homomorphism, gamma, which acts from A to the algebra of continuous functions on the maximal spectrum. And this map takes every element little a of our algebra to the function A hat, given by the following simple formula. If chi is a character, then A hat at chi is just chi evaluated at A. This is the Gelfand transform. So we proved several important properties of this map. In particular, this is a Banach algebra homomorphism, so it is bounded, and its norm is at most 1. In some sense, the Gelfand transform is a standard way of making an arbitrary commutative unital Banach algebra into a function algebra. So in some sense, what we are trying to do, we are trying to embed A into the algebra of continuous functions. In general, this map is not injective. It may have a non-trivial kernel, and in fact, the kernel is nothing but the Jacobson radical. The Jacobson radical is the intersection of all maximal ideals. But if A is Jacobson semi-simple, if the Jacobson radical is trivial, then gamma is injective. So in some sense, in this case, A becomes a subalgebra in the algebra of continuous functions. Okay, but now an initial question is, what if A is already a Banach function algebra? Suppose that A is a subalgebra in C of X, where X is a compact Hausdorff topological space. So let's now try to understand how this machinery works for this special case for Banach function algebras. So we're going to discuss the Gelfand transform of subalgebras of C of X. Roughly what we are going to do is to show that if A is contained in C of X, where X is a compact Hausdorff space, and if A satisfies some reasonable conditions, then the maximal spectrum of A can be identified with X, and under this identification, the Gelfand transform becomes just the inclusion of A into C of X. So this is our goal. Okay, so let's suppose that X is a compact Hausdorff topological space. Well, let's introduce some notation. For every point, a little x, in our space, we consider the evaluation character. We denoted it by epsilon x. This is the character of C of X, which takes every function f to f of x. Clearly, this is a character of C of x. And we let mx denote the kernel of the evaluation character. So obviously, this is a maximal ideal of C of x. And we have the following lemma. For every proper ideal I of C of x, there is a point x in our space such that I is contained in mx. So in other words, for every proper ideal in C of x, there is a point where all functions in I vanish. In some sense, this lemma can be interpreted as a kind of weak Nullstellen Satz for C of x. The proof is rather easy. Suppose this is not the case. Let's assume that this is wrong, and assume that for every point x in our space, we can find a function fx in the ideal I, such that this function doesn't vanish at x. Well, the function is continuous, and this assumption implies that f doesn't vanish on a neighborhood of x. So by continuity, there is a neighborhood ux of x such that fx of y is not equal to 0 for every y in this neighborhood. Now we use the compactness assumption. X is compact. So by the compactness of x, we see that x is covered by finitely many such neighborhoods. So x is the union of finitely many open sets uxi from 1 to n. And let's now consider the following function, denoted by f. F is given by the following simple formula. The sum of the absolute values, the squares of the absolute values of our functions, fxi. I claim that this function belongs to I for the following simple reason. The square of the absolute value of a complex number is the product of the complex conjugate and fxi itself. So fxi sits in the ideal, so this product is also in the ideal, and the sum is also in the ideal. So as a result, we see that f sits in I. F sits in I, but since every summand is strictly positive on the respective neighborhood, we conclude that f is strictly positive everywhere. By construction, it is strictly positive everywhere. So it is an invertible element in C of x. F is invertible in C of x. So our ideal contains an invertible element, which means exactly that actually I equals C of x. I equals C of x. And this is a contradiction because I was assumed to be a proper ideal. So the contradiction completes the proof. So as a corollary, we see that we have actually described all maximal ideals of C of x. More exactly, the map that's denoted by epsilon from x to the maximal spectrum of C of x, which takes every point x to mx, is a bijection. Or equivalently, if I identify the maximal spectrum with the character space, C of x hat, then this map takes every point little x to the evaluation character epsilon x. And this is a bijection. Well, indeed, we already know that every ideal I is contained in mx for a suitable x. So if I is already maximal, then I equals mx. This means that this map is onto, it is surjective. But on the other hand, it's a standard fact of general topology that continuous functions separate the points of x. And so this map is injective. As a result, it is a bijection. Okay. Let's now introduce some notation. So before we describe the Gelfand transform of C of x and of some related algebras, let's introduce the following notation. Suppose we have two compact Hausdorff topological spaces x and y, compact Hausdorff topological spaces, and a continuous map f from x to y. Then every continuous map induces an algebra homomorphism, which will be denoted by f dot. It acts from C of y to C of x by the following simple formula. It takes a continuous function phi on y to the composition of phi and f. So this is now a continuous function on x. And here are some simple properties of this construction. First of all, I claim that f dot is a unital algebra homomorphism, which is immediate from the definition. Second, the norm of this homomorphism is 1. Well, 1 except for the trivial case where either x or y is empty. If one of them is empty, then, well, then C of y or C of x is the zero algebra, and f dot is the zero map. But if they are non-trivial, then the norm of f dot is 1. This is also clear because on the one hand, it's clear that the supremum of this function, f composed with phi composed with f, is at most the supremum of phi. We have an inequality here. But on the other hand, if phi equals 1, then the norms are the same, and therefore the norm of f dot is exactly 1. And property 3, you have two continuous maps, f and g, f from x to y, and g from y to another compact space z. Then the homomorphism induced by their composition is equal to f dot composed with g dot. This is also immediate from the definition. Actually, all these properties mean that what we've just constructed is a contravariant functor from compact spaces to Banach algebras. But, well, we'll discuss this functor a bit later. At this point, let's only observe that that the above properties 1, 2, and 3, imply that if f is a homomorphism, then f dot is an isometric isomorphism. F dot is an isometric isomorphism. Well, indeed, if f is a homomorphism from x to y, then we have the inverse map f inverse, which acts from y to x, and it follows from this equation that f dot and g dot are inverses of each other. On the other hand, the norm of each of them is 1, and if now we have the obvious observation that if we have two bounded linear maps between normed spaces, which are inverses of each other, and norms of each of them, the norm of each of them is at most 1, then actually both of them are isometries. This is more or less trivial from the definition of the operator norm. So if f is a homomorphism, then f dot is an isometric isomorphism. And we now have the following theorem. Suppose that X is a compact Hausdorff topological space. And suppose that A is a subalgebra in C of X. Subalgebra, which contains the identity of C of X. That is, the function which is identically 1 belongs to A, so it is a unital subalgebra. And let's also suppose that A satisfies the following conditions. Condition 1, we suppose that A is a Banach algebra. Is a Banach algebra under a norm which is not necessarily induced from C of X, but which dominates the supremum norm. dominates the supremum norm. A typical example to keep in mind is the algebra of continuously differentiable functions on the closed interval, C1 of AB. This is a Banach algebra for its own norm, but its own norm is strictly stronger than the supremum norm. This is a typical example of an algebra satisfying this condition. Condition 2, we assume that A separates the points, of X. The question? No? Oh, okay. So I separate the points, which is also a rather natural condition. And condition 3 is that for every character chi of A, so every character is the evaluation character. For every character, there is a point such that chi equals epsilon x. Well, epsilon x restricted to A, but I use the same notation, epsilon x. I claim that if these conditions are satisfied, then the map epsilon, which acts from X to the maximal spectrum, and which takes every, well, better, at this point, it will be more convenient to interpret the maximal spectrum as the character space, a hat. So it acts from X to a hat and takes X to epsilon X. So this map is a homeomorphism. And moreover, the following diagram commutes. And the following diagram commutes. So this is the diagram. This is our algebra A. So A is included in C of X by assumption. This is just the inclusion map. On the other hand, we have the Gelfand transform of A, gamma A, which acts from A to the algebra of continuous functions on the maximal spectrum. And finally, this homomorphism between X and the maximal spectrum induces an isometric isomorphism epsilon dot from here to here. Epsilon dot is an isometric isomorphism by our previous observation. So this diagram commutes. So in other words, this picture means that X can be identified with the maximal spectrum in such a way that after we identify them, the Gelfand transform becomes exactly the inclusion map of A into C of X. This is the meaning of this result. So let's now prove this result. First of all, let's look at conditions 2 and 3 and observe that 2 and 3 together mean exactly that epsilon is a bijection. Well, indeed, property 3 means that epsilon is surjective, and property 2 means that epsilon is injective. So we know that epsilon is a bijection. Let's now prove that epsilon is continuous. To prove the continuity, let's recall one of the simplest properties of the weak star topology, which was discussed at the previous lecture. By this property, epsilon is continuous if and only if its composition with the evaluation maps, with all the evaluation maps, all these compositions are continuous. Or more exactly, this means that for every A and A, the map which takes X to epsilon of X evaluated at A is continuous. This is one of the basic properties of the weak star topology. But what is epsilon of x evaluated at A? This is just A of x. And little a is a continuous function. A is continuous by assumption. So we see that this condition is satisfied, and so epsilon is continuous. Epsilon is continuous. So epsilon is a continuous bijection. And now we again use a compactness argument. A continuous bijection between compact Hausdorff spaces is a homeomorphism. So the compactness of our spaces implies that epsilon is a homeomorphism. So to complete the proof, we must prove the commutativity of the diagram. And this is quite straightforward. So we compose epsilon dot and gamma. We apply it to an arbitrary element little a. And we evaluate this function at little x. So we want to show that this is nothing but a of x. So what is this? First we use the definition of epsilon dot. So by definition of the map epsilon dot, this is the function gamma of a evaluated at epsilon of x, that is epsilon x. Now we use the definition of the Gelfand transform. So the Gelfand transform of a evaluated at epsilon of x is just epsilon of x evaluated at a by the definition of the Gelfand transform. And this is just a of x. And that's it. So this equality shows that the diagram is commutative. And this completes the proof. So once again, the theorem means that if these conditions are satisfied, and actually they are very natural, there are many reasonable Banach algebras which satisfy all these conditions. So under these conditions, the spectrum of x, the spectrum of A is homeomorphic to x, and the Gelfand transform is just the inclusion map. And here is a simple special case, so a corollary. If A is exactly C of x, if A equals C of x, then the Gelfand transform is an isometric isomorphism. An isometric isomorphism. And its inverse is given by epsilon dot. This is immediate from our diagram, because in this case, this arrow is just the identity map of C of x onto itself. So the composition of these two maps, gamma and epsilon dot, is the identity map. And we already know that epsilon dot is an isometric isomorphism, and so epsilon dot is exactly the inverse of gamma. And since epsilon dot is an isometric isomorphism, this implies that gamma is also an isometric isomorphism. Okay, let's now discuss a very simple but important functorial property of the Gelfand transform. Functorial properties. Of the Gelfand transform. So let's consider the following two categories. The first category will be denoted by comp. So the objects of this category are just compact Hausdorff spaces. Compact Hausdorff topological spaces. And morphisms are continuous maps. And the second category will be denoted by cuba. The objects are commutative unital-Banach algebras. Commutative unital-Banach algebras. And the morphisms are continuous algebra homomorphisms. Continuous algebra homomorphisms. So these are our categories, and they are related by the following two functors, two contravariant functors. The first functor will be denoted by C. It acts from compact Hausdorff spaces to commutative unital-Banach algebras. And this is exactly the functor which we've just constructed here. So it takes every compact Hausdorff space X to the algebra of continuous functions, C of X. So this is this is the action of our functor on the objects. So we must now define our functor on the morphisms. So if F is a continuous map from X to Y, where X and Y are compact spaces, then our functor takes this map to the induced homomorphism F dot from C of Y to C of X, given by this formula. So it takes every continuous function phi to phi composed with F. So clearly this is a contravariant functor. The second functor functor acts in the opposite direction from cuba to comp. It will be denoted by max. And this functor takes every commutative unital-Banach algebra A to its maximal spectrum. So this is the action on the objects. Now we must define our function, our functor on morphisms. And if we have a morphism, that is a Banach algebra homomorphism from A to B, that's denoted by phi, then max takes this map to phi star, which acts from max of B to max of A. And it acts by the following simple formula. Phi star of chi equals chi composed with phi. So again, here we interpret the points of the maximal spectrum as characters. And clearly, if chi is a character of B, then chi composed with phi is a character of I. So this is well defined. The only question is, why is it continuous? To answer this question, let's recall that, let's first of all observe that phi star, defined here, is nothing but the restriction to the character space B hat of the dual map. Also denoted by phi star, so which acts from B star to A star. And this map is known to be continuous for the weak star topologies, which is weakly star continuous. The dual of a bounded linear map is weakly star continuous. So this is weakly star continuous, and so this one is just the restriction of this map to the character space of B. Okay, so this is a continuous map from the maximal spectrum of A, of B to the maximal spectrum of A. And clearly max is also a contravariant functor. So we have the following situation. We have two categories and two functors. This is the category of compact spaces. This is the category of commutative unital Banach algebras. C acts from here to here, and max acts from here to here. And these two functors are closely related. We have the following rather straightforward but important exercise. Part 1. So we have already constructed in this corollary homomorphism between X and the maximal spectrum of C of X. So we already know that this is a homomorphism. So that's denoted by epsilon X. But what I claim is that all these homomorphisms are compatible in the sense that they form a natural isomorphism of two functors. If X runs over the category of all compact spaces, then the collection of such homomorphisms is a natural isomorphism between the identity functor on the category of compact spaces and max composed with the composition of max and C. So the composition of these two functors is isomorphic to the identity functor. Now, what happens if we compose these two functors in the opposite order? First apply max and then apply C. And here's the answer. The Gelfand transform, if we consider the Gelfand transform of all commutative unital Banach algebras, so A runs over cuba, then the resulting family of algebra homomorphisms is a natural transformation. Is a natural transformation from the identity functor on the category of commutative unital Banach algebras to C composed with max. I don't claim that this is an isomorphism, but this is a natural transformation between two functors. And part 3, these two families of maps are related by the following picture. There exists a natural bijection. Between the set of morphisms in the category cuba, commutative unital Banach algebras, from A to C of X, and the set of morphisms in the category of compact spaces from X to max of A. And this bijection is given explicitly as follows. If we start with a homomorphism phi from A to C of X, then the corresponding map is constructed as follows. First, we apply epsilon X, and then we compose it with phi star. So epsilon X acts from X to the maximal spectrum of C of X, and phi star takes the maximal spectrum of this algebra to the maximal spectrum of A. So the resultant map is indeed a map from here to here. And the inverse map is also given by an explicit formula. If F if f is a continuous map from here to here, then we do the following. We first take the Gelfand transform, gamma A, and compose it with f dot. Again, so f acts from here to here. So the Gelfand transform of A acts from A to the algebra of continuous functions on the maximal spectrum. And after we apply f dot, we get a function in C of x. So indeed, this map is a homomorphism from here to here. So I claim that these two arrows are inverses to each other. And this is an explicit calculation. This is a very simple and straightforward exercise. Why is this useful? Actually, we meet a very standard category theoretic notion of an adjoint pair. To see this, let's replace the category of compact spaces by the opposite category. So the objects of the opposite category are the same, and the morphisms act in the opposite direction. So which simply reverse all the arrows. So in the opposite category, this set is the set of morphisms from max of A to X. If we now look here and here, what we get is that the functor max and the functor C form an adjoint pair. So hence this exercise implies that max and C is an adjoint pair of functors. Max is left adjoint to C, and C is right adjoint to max. So this is the category theoretic interpretation of the Gelfand transform. Our next goal will be to extend the theory of Gelfand transform to non-unital algebras. I have already said at the previous lecture, or maybe on the first lecture, that the non-unital case is also very important because many algebras which naturally appear, many Banach algebras and many C-star algebras which naturally appear in this theory are not unital. And we must somehow deal with such algebras. So before we extend the Gelfand theory to the non-unital case, let's briefly discuss a simple but useful trick which makes an arbitrary algebra into a unital algebra. The trick is called the unitization. Suppose we have an algebra, A, not necessarily unital. But so A is not assumed to be Banach algebra. This is just an algebra. And let's denote by A plus the direct sum. This is the direct sum in the class of vector spaces of A and the one-dimensional space spanned by a single element denoted like this. This is a vector space direct sum. So in some sense, we join a new element to A. Now we define a multiplication on the space in such a way that this new element becomes an identity. Clearly, this is the only reasonable way of defining such a multiplication, so we must explain what is the product of two elements of the following form, where lambda and mu are complex numbers. And the only reasonable way to define this product is to define it as follows: AB plus mu A plus lambda B plus lambda mu 1. elements of our algebra, and lambda and mu are complex numbers. It's rather easy to show that this multiplication is associative. So A plus becomes an algebra, a unital algebra. A plus becomes a unital algebra. And this algebra is called the unitization of A. A plus is the unitization of A. The unitization has the following simple universal property. This is our proposition 1. Actually, a proposition and an exercise at the same time. Proposition exercise 1. Suppose that A is an algebra and B is a unital algebra. A unital algebra. Part 1. For every algebra homomorphism phi from A to B, define a map phi plus from A plus to B by the following formula. So in other words, phi plus extends phi from A to A plus, and it takes the identity of A plus to the identity of B. I claim that phi plus is also an algebra homomorphism. And moreover, this is part 2, this construction gives us a bijection. There is a natural bijection. A natural bijection between the set of all algebra homomorphisms from A to B, and the set of all unital algebra homomorphisms from A plus to B. And this bijection works as follows. If phi is a homomorphism from A to B, then the corresponding homomorphism phi from A plus to B is just phi plus. And the opposite map from here to here, takes every homomorphism psi from A plus to B and restricts it to A. And these two maps are inverses of each other. This is a very simple exercise. So basically, this exercise gives us a universal property of the unitization. And a similar result holds for Banach algebras. This is proposition exercise 2. If A is a Banach algebra, then its unitization, A plus, is also a Banach algebra. Is a Banach algebra with respect to the following norm. So we define the norm of A plus lambda 1 to be the following sum. The norm of A plus the absolute value of lambda. This norm is easily seen to be submultiplicative. And moreover, proposition 1 holds for Banach algebras. If we consider only continuous homomorphisms, in particular if hom stands for the set of all continuous homomorphisms. In other words, if A and B are Banach algebras and phi is continuous, then phi plus is also continuous, and we have a bijection between the set of continuous homomorphisms from A to B and the set of all continuous unital homomorphisms from A plus to B. So this is the universal property of unitization in the class of Banach algebras. Okay, here is, so this looks like something trivial, but sometimes it's very useful. Here is a simple illustration, the corollary of this result. If A is a Banach algebra, then every character of A, chi of A, is continuous, automatically continuous, and the norm of chi is less than or equal to 1. Well, indeed, we have already proved this at the first lecture under the assumption that A is unital. And now we know, now we can observe that this is also true for non-unital algebras, because the character of A extends to a character of its unitization by this formula. And this extension is continuous. And so clearly the restriction of a continuous map to A is also continuous, and its norm is less than or equal to 1. Okay, let's now look how this construction looks like in the special case, in the following special case. An example and an exercise at the same time. Suppose that X is a locally compact Hausdorff topological space. We want to describe the unitization of the algebra C0 of X, of continuous functions vanishing at infinity. And to do this, let's denote by X plus the one point compactification. The 1 point compactification of X. Well, let's briefly recall how it is constructed. So as a set, X plus is just the disjoint union of X and a single point denoted like infinity. And the topology on X plus is defined as follows. First of all, it contains all open sets in X. So all open sets in X are by definition open in X plus. And also we consider the following neighborhoods of infinity. So an open set containing the infinity is X minus K, where K is a compact subset, X plus minus K, where K is a compact subset of X. So this is a typical neighborhood of infinity. So then by definition, this collection of subsets of X plus is the canonical topology on the 1 point compactification. And let's recall the following standard fact, that first of all, X plus is compact and Hausdorff. Compact and Hausdorff. And the inclusion of X into X plus is a topological embedding. Topological embedding. In other words, the topology on X induced from X plus is equal to the original topology on X. And the second fact, roughly it states that this is the only reasonable way of adding a point, of compactifying X by adding a single point. More exactly, if Y is a compact Hausdorff topological space, And if x is equal to y minus a single point y0, then x is locally compact. X is locally compact. And we have a homomorphism. There is a homomorphism between x plus and y, which takes every point of x to itself, and which takes infinity to y0. Topological embedding, well, it's an injective map. Clearly, it is injective. The point is that if we equip x with a topology induced from x plus, then this will be equal to the original topology on x. So this is not only continuous, but actually this, the fact that it is a topological embedding means that two natural topologies on x are the same. The original topology and the topology induced from x plus. So the intersection, more exactly, the intersection of any open set in here with x is open, and conversely, the image of an open set here is open. Is open here, just by the definition, by the way. So this is more or less immediate from the construction of the topology on x plus. Okay, so this is these are some standard facts on the one-point compactification. And now let's look at the algebra C0 of x of continuous functions which vanish at infinity. So what is the exercise? I promise that this will be an exercise. The exercise is the following. Prove that C0 of x, the algebra of continuous functions vanishing at infinity on x, consists precisely of those functions on x which are the restrictions to x of those continuous functions on the one-point compactification which vanish at infinity. Satisfying this condition. So in other words, we may say that a continuous function vanishes at infinity in the sense of our definition, even only if it vanishes at infinity, literally. And this fact easily implies the following. We have a topological isomorphism. Between the unitization of C0 of x and the algebra of continuous functions on the one-point compactification. And this isomorphism is given by the following formula. It takes f plus lambda 1, where f is in C0 of x, to f plus lambda, where we assume that f is trivially extended to the one-point compactification by the following formula. I don't claim that this isomorphism is isometric. In general, this is not true. But this is an algebra isomorphism, and it is a homomorphism of these algebras. At the next lecture, we will see how to make this isomorphism isometric. The announcement is that the standard norm on the unitization doesn't work. Where is it? So if we introduce this norm on the unitization, then this isomorphism is not necessarily isometric. But there is another standard way of putting a norm on the unitization of any C-star algebra. And under this norm, this isomorphism will be isometric. This will be proved at the next lecture. Okay. Okay, let's now come back to arbitrary non-unital algebras. So by using unitizations, we can now define the spectrum of any element in any algebra, not necessarily unital. So suppose that A is an algebra and little a is an element of A. We define the non-unital spectrum, of little a as follows. This is a set denoted by sigma prime of A, and we define this set to be the spectrum of A in the unitization of A. Well, this is a subset of the complex plane. But what if A is already unital? If A is already unital, then we see that there are two spectra of A, the usual spectrum and the non-unital spectrum. It's natural to conjecture that probably they are compatible, they are the same. But this is not the case. This is not the case, and this follows from the following observation. Let's observe that any algebra A is a two-sided ideal in its unitization. Is a two-sided ideal. As a result, we see that any element in our algebra A is not invertible in A+. Every little a is non-invertible in A+. Because an element of a proper two-sided ideal is never invertible. So as a result, we see that the non-unital spectrum always contains 0. Always contains 0. And in particular, if A is already unital, then it can happen that the spectrum and the non-unital spectrum are not the same. 0 is already in the non-unital spectrum. Well, this is a bit unfortunate, but we will see now that for unital algebras, 0 is the only difference between the spectrum and the non-unital spectrum. More exactly, we have the following simple exercise. Exercise part 1. Suppose that we have two unital algebras, A and B, unital algebras. We consider their direct sum, and we take two elements, A and B and B. Then the spectrum of a pair little a, little b in their direct sum is equal to the union of the spectrum of A and the spectrum of B. In fact, this is trivial. Everything reduces to the fact that a pair A and B is an invertible element if and only if both A and B are invertible. Now, this really implies this equality. Exercise 2. Suppose that A is a unital algebra. What can we say about its unitization then? I claim that there exists a unital algebra isomorphism between the direct sum of A and the complex numbers and the unitization of A and A plus. And this isomorphism is given by the following formula. It takes every pair A and lambda, and this direct sum, to the following element of the unitization. A plus lambda, well, the natural choice would be like this. And clearly this is a vector space isomorphism for obvious reasons. But this is not an algebra homomorphism. And to make it into an algebra homomorphism, we must modify it as follows. We multiply lambda by the difference of two identities, the new identity and the old one. And a straightforward calculation shows that this is indeed an algebra isomorphism. So as a result, we see that if A is unital, then its unitization is isomorphic, not only as a vector space, but also as an algebra to the direct sum of A and the complex numbers. And if we now combine this with observation 1, we conclude that if A is a unital algebra, then for every element little a, the non-unital spectrum of this element is the spectrum, the union of the spectrum and 0. This is immediate from this isomorphism and from part 1. So 0 is the only difference between the spectrum and the non-unital spectrum. This formula enables us to define the spectral radius of any element in a not necessarily unital Banach algebra. And the definition is more or less straightforward. Suppose that A is a Banach algebra, and little a is an element of A. We define the spectral radius of A as follows. This is the supremum of the absolute values of lambda, where lambda runs over the non-unital spectrum. The previous formula implies that this definition is consistent with the unital case, because if A is already unital, then 0 is the only difference between the spectrum and the non-unital spectrum, and clearly the supremum, so 0 doesn't affect the supremum. If we remove the prime here, the supremum will be the same. Ну, определение вот. The definition of sigma prime works for any algebra, not necessarily unital. Formally, the construction of the unitization applies to any algebra. So if we don't know is it unital or maybe it is not unital, but in any case, the unitization works. This construction is well defined. So in principle, we can consider the unitization of a unital algebra. And the point is that the unitization of a unital algebra is isomorphic to this direct sum as an algebra. And as a result, the spectrum, the non-unital spectrum, and the spectrum are related by this formula. Clearly, the supremum of this set and the supremum of this set are the same. And as a result, this new definition of the spectral radius, on the one hand, this new definition works for any Banach algebra, not necessarily unital. But on the other hand, if A is already unital, then these two definitions are consistent. Okay? Okay, so the spectral radius is given by the following formula, and the Berling-Gelfand formula for the spectral radius readily extends to arbitrary Banach algebras, not necessarily unital. So the spectral radius is equal to the following limit. Or equivalently, we can take the infimum, and the result will be the same. Well, indeed, we simply apply this formula to the unitization of A, and we get this result. Okay. Okay, now we can extend. Oh, we have no time to extend. Maybe. I forgot what is the time. We must finish in a minute. Yeah, in 3 minutes. Well, 3 minutes is not enough. Okay, so that's all for today. At the beginning of the next lecture, we extend Gelfand's theory of commutative Banach algebras to the non-unital case. Now I'll just make a little announcement. So the principal difference between the unital case and the non-unital case is that the maximal spectrum, first of all, we will define it in a slightly modified way. In the non-unital case, the maximal spectrum, the good definition of the maximal spectrum is different. It consists not of all maximal ideals, but only of those maximal ideals which are modular. This is a specific property which will be discussed in the next lecture. So the maximal spectrum is now defined to be the set of all maximal modular ideals. It is not necessarily compact, but it is locally compact. It is locally compact and Hausdorff. And the Gelfand transform of a non-unital Banach algebra acts from A to the algebra of continuous and vanishing ad infinity functions on the maximal spectrum. But the basic properties of the Gelfand transform are more or less the same as in the unital case. So this will be done at the next lecture, and then we will begin to discuss sister algebras. And as I promised at the previous lecture, we will see that if A is a sister algebra, if A is a commutative sister algebra, we will prove that the Gelfand transform is an isometric isomorphism. This is one of the fundamental results in the sister algebra theory. Okay,